All right, if you're studying software engineering, you have absolutely heard of object-oriented programming, or OOP. But what is it, really? In the next few minutes, we are going to completely demystify it. We're going to break down exactly what you need to know from the core ideas to how you actually use it. So let's just dive right in.
Here's the plan. First, we'll talk about why OOP even exists. Then, we'll get into the essential tools you'll be using. After that, we'll learn how to read the blueprints of a system, how to turn those designs into solid code, and we'll wrap up with a little checklist to make sure you've got it all down.
So, to really get why OOP is such a big deal, we have to go back to the beginning and understand the problem it was actually built to solve.
I mean, why change it all, right? Well, it's because as software got bigger and way more complex, the old ways of writing code just started to fall apart. It was becoming a tangled mess, super hard to manage. We needed a better way to handle all that complexity.
And here is the fundamental shift, the big idea. The old way, procedural programming, kept your data and the functions that operate on that data totally separate. And this, well, it could lead to some pretty gnarly, hard-to-track bugs. OOP's brilliant move was to say, hey, let's package the data and its related behaviors together into one neat little unit. That's it. This simple change gives you much clearer ownership and makes your code a whole lot more reliable.
Okay, so how does OOP actually do that? How does it package everything up? Well, it uses a core toolkit of concepts. Let's break down the big ones you absolutely have to know.
First up, we have the class. The best analogy for a class, hands down, is a blueprint for a house. The blueprint lays out the design, how many rooms, where the windows go, all that stuff. It defines the structure, but it's not the house itself, right? It's just the plan.
So if the class is the blueprint, then an object is the actual house you build from it. And you can build tons of houses from that one blueprint. My house might have blue walls, your house could have green walls. They have the same structure, but their specific data, their attributes, are totally unique. This leads us right to encapsulation. Think of this as the walls and the doors of the house. It's the principle of bundling that data and the methods together while protecting the internal complicated stuff from the outside world. It's like you don't need to know how the engine in your car works to drive it. You just use the steering wheel. Encapsulation gives you a safe, public way to interact with an object while hiding all the messy details. This makes your code so much safer.
Next up is inheritance. This is an incredibly powerful way to reuse your code. Imagine you have a general account class. Well, you can create a more specific savings account that inherits everything the account has, but then adds its own special features, like a way to apply interest. This creates what we call an is-a relationship. A savings account is a type of account.
Now this one sounds complicated, but the idea behind it is actually beautiful. Polymorphism. It literally means many forms, and it's all about making your code more flexible. The key phrase to remember here is one interface, many implementations. You use a single command, but different objects can respond to that same command in their own unique, specific ways.
Think about this. Let's say you have a bunch of different shapes, circles, squares, triangles. You can just go through the list and tell each shape to draw itself. The circle object knows how to draw a circle. The square knows how to draw a square. You, the programmer, don't have to check what kind of shape it is and write a bunch of if statements. You just send the same message, draw, and polymorphism takes care of the rest. It's awesome.
Okay, so that's the core theory. Now let's get practical. Let's learn how to actually read the visual language of OOP, which is the class diagram.
So a class diagram is basically a map of your system. Each box is a class, and inside you'll see its data, or attributes, and its behaviors, or methods. The really important things to look for are the lines and arrows connecting them. The arrows show inheritance. They always point from the child up to the parent. And the simple lines show how different classes are connected to each other.
You're also going to see these little plus and minus symbols everywhere. They're all about visibility. A plus sign means something is public. It can be accessed from anywhere in the code. A minus sign means it's private, hidden away for the class's own internal use. This is literally how a diagram shows you encapsulation in action.
So, picture this. You're in an exam or an interview, and someone puts one of these in front of you. What do you say? Here's your 3-step game plan. First, find an inheritance arrow and just state the obvious. Okay, this class is the child of this parent class. Done. Second, find a plus and a minus. Point to them and say, this is a public method and this is a private attribute. And third, find a line connecting two classes and explain the relationship, like, this shows that one customer can have many orders. That's it. You've just proven you can read the blueprint.
All right, we can read the blueprints. Now let's talk about actually writing the code. How do we make it clean, effective, and something that other people can actually understand? You know, good design doesn't have to be super complicated. It starts simple. First, what are we trying to build? Once you know that, look for the main things or nouns in the problem description. Those are usually your classes. Then for each class, you just ask two questions. What does this thing know? Those are its attributes. And what does this thing do? Those are its methods. Finally, you just figure out how they all need to connect to each other.
So what does good OOP code even look like? Well, it's easy to read. Each method does just one thing. Your class and method names actually describe what they do. Your classes are small and focused. And you're always protecting your data by keeping things private unless they absolutely need to be public. Sticking to these rules makes your code so much easier to work with down the line.
We have covered a ton of ground. So this last section is all about pulling it together with a simple checklist you can use to really make sure you've locked in these concepts.
And remember, writing the code is just the start. You have to test it. In OOP, we do this at different levels. Unit tests check one tiny piece, like a single method, to make sure it works perfectly. Then integration or subsystem tests check that a few classes can work together correctly. And finally, system tests check the whole application from start to finish to make sure it all comes together as expected.
So here it is, your final check-in. Can you define these basic terms? Can you explain the big three concepts in your own words? Can you read a basic class diagram? You might even want to pause here and really quiz yourself. If you can confidently talk through every point on this list, then congratulations, you have built a truly solid foundation in object-oriented programming.
We've broken down the concepts and we've laid out the best practices. OOP isn't just a bunch of academic theory. It's a really powerful way of thinking and organizing complexity so you can build incredible software. So the only real question left is, now that you have this framework, what are you going to build?